Hi everyone, welcome to my channel. Today we will see how to create sentence embedding and how to use those sentence embedding for applications like sentence similarity, semantic search and clustering. So what is sentence embedding? You can think of sentence embedding is a natural language processing techniques which convert your text or sentences into the vector representation. Here you could say this is one of the image where you could see we have a sentences here and we are converting those sentences into the vector representation, and once you have your text or sentences represented in a numerical or vector representation, then you can do all sort of mathematical operations to find whether two sentences are similar or not, whether how much semantically similar them. You could cluster them on the basis of their numerical representation. So the good embedding you can think of, if there are two sentences has some semantic similarity in the real world, then we also think that their vector representation should also have that similarity. So if I take the dot product of those two vectors, I should find the dot product of the two vectors representing to the similar sentences should be a higher, whereas if the two sentences are unrelated in the real world, they should have a less similarity in the context of the dot product. So we will be using a sentence transformer library to calculate the embedding of our sentences, to calculate that numerical representation. So first thing we will do, let's install the sentence transformer. So we will use the pip install, and it will simply install the sentence transformer. Okay, you could see it has installed. If you already have it, it's not going to install it again. So once you have a sentence transformer installed, you can import the sentence transformer and some utility from it, and it requires a model that it needs to create those embeddings. So that model is nothing but some kind of transformer based model. So if I search this particular model, then you will see this is one of the transformer model hosted on Hugging Face from the sentence transformer. So you could use, what are the models available on Hugging Face Hub. There are many models actually created or optimized from the sentence transformer. There are list of models they have. If you go to their profile on Hugging Face, you could see a lot of different models they have created. You could see there are 124 different models, and even you could use the models from the other users, need not to be from the sentence transformers. So you need any model to do a particular, to calculate an embedding. So here we are using this all that particular model. You could read more about this model, what it does. This model is good for mapping sentences or paragraph into a particular vector dimension, and you could also read up more about that particular model here in the description. So what we're going to do, we're going to use that model as our sentence transformer, right? And then we can pass our sentences. Let's say we have these two sentences, we're going to pass those two sentences to this particular model. So that model has an encode method. So let's first import this thing, because that model is not available locally. It needs to download from this Hugging Face hub. From here it's going to download that model. Since I had already downloaded, or when you install sentence transformer, there are certain models that comes with the default. So now once we have this model, see, this model is nothing but the sentence transformer instance. So this is the sentence transformer instance, and it will have that information, the kind of model it is. So let's use this model now to calculate embedding for those two sentences. So we're going to use the model.encode method, which is going to take the list of sentences what we have. We don't know this thing, yeah, the list of sentences it has. And then what it is going to do finally, once these embeddings are there, we're just going to iterate through this embedding on our sentences to just see what sentence, what embedding we got. So let me run this thing and see, it has calculated some embeddings. So if I go, you could see first we are printing the sentence what we have, and then we are printing embedding. Now you could see embedding is nothing but just some vector representation, and it's really difficult to understand what those numbers mean that we as a human can't interpret those numbers. So here is the other sentence, and you should find this particular embedding. Then how do we know the number representation we got is something meaningful or not, right? Since we can't interpret those numbers, but we could definitely check its application. And as I mentioned earlier, if there are two sentences, let's say if those two sentences are related to each other in the real world, then we expect their numerical representation show that that particular relatedness. So let me clear this output. Now, since we have an embedding, nothing but the vector representation, we can perform some mathematical operations on it. And one of the popular mathematical operations to check the similarity between vectors is the cosine similarity. So we're going to use cosine similarity from the utils. If you could remember, on the top, we have imported a sentence transformer class and also the utility class. Now that utility module has this cosine similarity function, which takes the embedding of two sentences, and then finally it tells you what is the cosine similarity. So let's have these two sentences. So we have the same model, what we have on the top. We're going to encode this sentence. Let's call it I am eating apple, and then I like fruits. And then it's going to calculate the similarity between these two sentences. So seems to be similarity is 53%. Those two particular sentences are similar. So what we will do next? We will take a couple of sentences. So I have this couple of sentences, and some of these sentences are related to each other, and some of these sentences are not related to each other, right? And then what we will do? We're going to pass the same sentences again to the encode method of the model, get their embedding, and then we will pass that whole embedding. We want to know how does this sentences related to each other. So this embedding we are passing twice to the cosine similarity. It means what? We want to know how each of the sentence embedding is similar to each of the other sentences, and that's what the matrix is going to calculate. So let me run this thing, and you could see cosine similarity. This is nothing but the matrix because we have multiple sentences, right? So what it tells here, if you look at the zeroth row and the zeroth column here, which has a value 1 because it is the similarity with itself. But then you could see the similarity between the first example and the second example is the 75%, because we can get or you can think of some metric, need not to be just 75%. Let's say it is 0.75. So you could see the first sentence, which is a man is eating food, and the other is also a man is eating a piece of bread. Now both are things related to eating. That's why they have the higher similarity. But if you look at the first sentence and the third sentence similarity, it's almost negative because they are not at all related to each other. Okay, but let's look at then the third sentence here, with which sentence it is much more similar. So you can think of the third sentence is similar to itself, that is the highest that we could see. But there are no other sentences. Okay, better be, we have down the code where we check which sentence is more similar to other sentence. So let's use this particular similarity matrix what we have. So what we will do, we want to find out which sentence is the most similar to the other sentence. To do that thing, we will iterate through our matrix, this thing. Okay, we will do two for loop. And what we will do, we will collect all these possible values, that nothing but how much first and second sentence is similar. We will put it in our list. We will check how much first and third sentence is similar, and we will put it in our list. That's what we are doing here. So we are just iterating through this particular matrix and collecting the pairwise similarity. This is what we got once we go through it. So you could see the similarity between the first sentence and the second is 0.75, whereas the first and the third one, because index starts with 0, is something like this. So you now have similarity between the all pairs of the sentences that you have. Now once we have this list of tuples, okay, which is nothing but those three values, what we want to do, we want to sort this particular thing with respect to the score, the similarity score, because we care about only the top similar pairs we want. So let's iterate through this list. So before iterate through, okay, what we want, actually we want to sort it. So we take this particular thing, a list of tuples what we have, but we want to sort by this value. So in the sorted function, we can give the key. Key is nothing but when you want to sort this particular elements or objects inside this list, what criteria you should use. That key is nothing but the criteria. So what we are specifying, that given any element in this list, we want to sort by the first sub part of that particular element. So this element is a tuple. So if that element we call it as a x, we want to sort by the zeroth element, which is nothing but the score. That's what the sorting is going to do. And then once it is sorting, we just want to see the top five pairs, right? So the top five pairs is nothing but we will get the score and the index of the sentence, and we can get that actual sentence using this sentence dictionary, because you could see on the top we have a list, right? So we can pass the index of the sentence and we should get the sentence back. So let's do that thing. Let me run this thing and see we are printing. The first it sorted all of these things, and then finally we printed the top five similar pairs. So you could see the first most similar pair is the man is eating food, and this is also related to the man eating something that got the highest similarity. And then you have the man riding horse, and this is also related to some man riding some particular horse, so that's why they got the highest similar. So you could see how powerful these embeddings are there. This sentences has a certain meaning in the real world. We know that these two sentences represent the eating, so even their numerical representation what we got using the embeddings, those real world meaning or that particular similarity is still what you can, it is still there in the numerical represent. And this is how we could see which kind of embedding technique is better. The embedding technique which is able to preserve that meaning from the real world inside that numerical representation, that is something we're going to prefer. So now we have a capability to generate the what you call the numerical representation of the sentence, and we could also compare those sentences and see how similar those sentences are. So that was our first application to looking at the sentence similarity. Now let's look at the semantic search. You know, let me see what exactly the semantic search is nothing but, let's say you have a query and you have a bunch of document. Now the Google search is itself is a semantic search, right? You put your query here, and then Google goes through all the let's say web pages available on the internet, and then finds out which is the most semantically similar document that what we are searching for. And there are a lot of application. Okay, you might have, let's say, hundred or thousands of documents, and you when you want to find some particular information in that document, you can build a semantic search system which take your user input, which is a query that you are looking for, and then you can check it against all the documents what we have, and that's what we're going to see. So let's go back to our notebook and focus on the semantic search thing. Okay, think of this scenario. So again, now we will use the different model for the semantic search. So we use some model, and we saw this model was available from the sentence transformer on the hub. Now let's use something different model here. And which model to use here? You can always go to the Hugging Face hub and see which model you want to use for a particular application. So if I search this model, you will see it is coming from the user clips. Okay, and this is the particular model, and you can see this model is especially good for FAQ kind of things, so question answering kind of stuff. This model has been trained. So whenever you are working on an application, you can go here on the Hugging Face hub, look at the list of models are available, and you can find the most suitable model for particular application. And if you don't have sentence transformer, anyway we'll have a default model that they're going to use, and that is could be the best model. So let's say we're going to use this particular model to create the embedding for the application of question answering kind of thing. So you can think of, you have, let's say, three answers. These three answers you can think of, let's say there are three documents in your system. It could be three, it could be 3,000 document. And then you have some query whose answer can be found in this particular documents. But you want to know which document can have that particular answer. So what is the way to do? First, you can take your question and you can generate embedding for that question. And then you can also generate embedding for every document in your system. Currently, it's a 3, as I said, it could be 3,000. And then what you want to do? You want to do these two things: calculate embedding and then check the cosine similarity with each of the document there. The document having the highest cosine similarity is the one which is the semantically most similar to your query, and there is a chances the answer to your query is actually lies inside that document. And that's what we're going to do. But then these two steps, actually finding that particular cosine similarity and then ranking it, right? That's what the Google also does, right? When you search any query, first it's going to calculate some metric against each of the document available on the internet, and then depends on that score it's going to rank them. Now these two steps can be done using this function called semantic search. Just like cosine similarity, we have a semantic search function available in the utilities. You can use that semantic search. The semantic search takes your query and then your all document embeddings. Okay, so let's do that thing. I should have started this thing. So meanwhile, it would have downloaded that particular model because it might be, let's see. Okay, good thing that it is actually taking from my cache because I have uh, did some trial thing before I record this particular thing. So that is the reason you could see, you know, this is doing fast. But if I, try some other model, it might take some more time. So let's go to this particular, code snippet and run it, and let's see whether it is able to find this thing. So see what was our query. Our query was how many models can I host on Hugging Face? That is the user has a query. And then there are some information about that particular query. The first document says that all plans come with the unlimited private models and datasets. So this is definitely talking about the how many models you can host. Even the next document is talking about some kind of NLP models and this thing. So you could see all these three documents are quite similar with what user looking for. But if you read them carefully, the first document is actually the most similar to the answer that we can get for the query. And so, let me run through it and we will see what is the semantic score we got for each of these things. So for the first corpus ID, corpus 0, which is nothing but the first sentence here, we got the score of you know 0.56. For the second, we got 0.51, and for the other one, we got 0.7. So definitely, though all of the three documents here is almost similar, but you could see we got the highest score among them related to the document first, which is nothing but that it holds that answer unlimited. So this is how semantic search can be used. You can crawl through or go through all the documents in your system, and then we will check which is the most similar document with respect to your query, and you can fetch that particular thing. Now, this semantic search thing can be coupled with the question answering also, right? Now you could see semantic search has only tell us, that the answer is actually lies inside this particular document, but it didn't tell you what is the answer. It only narrowed down in your search. Instead of, let's say, thousands of documents, now it is telling you your answer could be here, but you still don't know what is that answer. So what you can do, whatever the output written by semantic search, this particular thing you can use with the question answering thing. Okay, maybe let's see if this video doesn't get long, I might show you how to do that thing. Why? Okay, let's do the now only. Let me go to the question answering from Hugging Face. Okay, let's go to the Hugging Face hub and we want to do a question answering kind of task. Do we have example here? Yes, let's copy this example. Where it is, here is our notebook, right? I wanted to show you that you can take this document and then you can give to the question answering, which can give you the exact answer. So you can let's say we want to use the Hugging Face pipeline, so we need to import it first from the transformer. Now I'm doubtful whether we have transformer installed directly, or either we have to install it. Since we have installed sentence transformer, it should be there. Yeah. So now you can use the question answering pipeline from the Hugging Face, right? Where you can give a question and the context, right? Let's try this thing on our example. Okay. Since it is sample example, let's try here because it will download that model first, right? If it is not there, you see, It started downloading now, and you could see it is like 240 MB model. So let's wait till it downloads, and once it downloads, it will run on this example, and we should see what kind of output it produces. So we have a question, where do I live? And the context, the document is having some information saying that it lives some place here. And you could see it has exactly find out what place the person is living. So this is what you could do. Now imagine we build a question answering system where someone can enter the query, and then you will find the questions inside your thousands of document. The limitation of this question answering system is that you can't put the context this all the thousands of documents that you have. No, this context needs to be smaller. So what semantic search will do? Semantic search is going to help you to narrow down your document. So instead of putting those 3000 documents inside this context, semantic search is going to tell you which is the most semantically similar document you have, so that you can put there. Now, given this particular question, right, let's put this here. Our semantic search has told the answer one or this document holds the more semantically meaningful whatever that answer located here. Right? Let me copy this now context. Let's make this thing as a context now. Okay, and let's run this thing and see whether we get the answer correct. We got, so you see, we got the answer called unlimited. That was the answer. This is how you can solve real world problems by putting two three models together or two three applications together. Now you could see here how many things we are using. First thing, we are using the sentence embedding, right? We are using that embedding to calculate the semantic similarity, and that is where we are able to narrow down the different documents and only selected the document which has the highest score. Now once you have already selected the document with the highest score, then you want to pick up that document, put it into your question answering system, and then question answering system will generate the exact answer depends on this document, right? So this is how. So this was something I didn't plan, but anyway. So yeah. So let's go to the next application. What we have, right? So the last thing I want to try is the clustering approach. We could see that it is able to create the high score for the documents which are similar to each other. Now we will see, if we pass this all these documents, how does it is able to cluster them the semantically similar document, and that is the next application we're going to see. So here I'm going to import the scikit-learn k-means, which is one of the clustering algorithm, and then I'm using the same model what I use on the topmost, because I just don't want to spend time downloading again that model, right? So let's use the same model, and then I have a bunch of sentences that we want to cluster together. So what we will do, this embedder is nothing but our that model. We encode, we call the encode, and we got the embedding for each of this sentence, right? This numerical representation. And then we will do one more thing. We're going to normalize this embedding. So that embedding is nothing but bunch of numbers, right? I think we have seen on the top. Let me see whether I cleared it, or yeah, you could see. No, I think this is similarity. So that embedding is nothing but some bunch of numbers, right? So what we want to do, we want to normalize that number. So that's why we are using the numpy, some linear algebra function to normalize those vectors. Since we know in the context of machine learning, if you normalize those vectors, it becomes easy for the distance based metric or optimization kind of thing. And here in the k-means, we're going to calculate the distance between these two vectors, right? So that's why we're going to normalize this thing. Even if you don't normalize, it's not going to matter much, but let's say we're going to normalize that embedding. So now we got embedding here. So this again, this will be just let me see. I think this will be the list, right? So let's take the first element in that list. Nothing but a bunch of numbers here, right? That we don't understand. So let's cluster these vectors now. So we're going to use this k-means. We're going to tell how many clusters. So there are different techniques to know, how many cluster to create. But let's say by looking at our data, we decided to create the three cluster. We want to group three. We want to create the three groups out of this sentences. And then this is our k-means model with the three cluster. Let's fit our data is nothing but the embedding that we have created here, right? This is the embedding, nothing but our feature engineering or the feature vectors. And then finally, once this data is going to fit to our model, it's going to assign some number to it. Now since we have three clusters, so this sentence will be either one of the three. So you, for each sentence you will get the number. Does it belong to the first cluster? Does it belong to the second? Or is it belong to the third cluster? That's what we're going to it. So let's fit the clustering here. Okay, now you could see for each sentence we got some number. So what it is telling, the first sentence and the second sentence went to the cluster number 2, whereas the third went to the cluster number 1. What are those cluster? This is hard to interpret. So let's do one thing. By the way, I got this this kind of example on some Stack Overflow question I'm putting here, because I'm going to put this particular notebook into the video description so that you can go and play around it. Yeah, what I was saying, this is hard to interpret, which sentences were. So let's, what we will do, we will create one dictionary. Okay, and in this dictionary, what we will do, let's say this cluster number 2, we will put all the sentences for that particular cluster into the one list, right? So if you look at, we're iterating through our cluster assignments, which is this, right? And so we get that cluster ID, this one, and some number associated with it, 0 1 2 3, the index of this particular list. Then what we will do, we will check, do we have already that particular cluster ID here? If not, we're going to initiate this dictionary with an empty list for that particular cluster. Okay, and then what we will do, inside this list for that particular thing, we're going to append our sentence here. So corpus is nothing but our list of sentences, and we're going to pass that index. So what is going to happen, let's say we are at here, what is going to happen, this will belong to the cluster 1, but the index of this particular list is 3 here. So we will go and we will pick up the third sentence, which is this one, and that sentence we go to that particular cluster. Maybe I run it, it will be much more clear. Yeah, this is what I mean actually. For each cluster in our dictionary, we got a key, and with respect to that key we have a list of sentences that we are putting here. Now let's have a look which went where. So you could see the cluster 0, which has sentences like, the girl is a crying baby, or sorry, the girl is carrying baby, sorry. Then the baby is carried by the woman, right? And what is the second? A monkey is playing drums. Someone, I think, some kind of mixture you see. The second, you see the horse is eating grass, the man is riding horse. So this one seems to be related to the animal, horse, and the man. And the next one you could see, a man is eating food, man is eating. So okay, so this cluster seems to be related, all the sentences related to the eating or the food, eating related stuff. The middle cluster is all related to the animal, horse riding, man kind of stuff. And this one is related to the baby, monkey playing something and kind of stuff. You could say there is a scope to separate these sentences. Maybe we need to create one more cluster. So let's say instead of three cluster, if I create the four cluster, how the sentences will get separate, right? So let me run this thing here. But now let me copy this so that we could see how output got changed, right? And then let me run this thing here. I take four, right? Let me see once again. Yeah, I did put four. So now let's look at, now we got the four thing, right? So we could see, okay, the man eating is still remain the same. That one cluster still hold all the eating related stuff. But you could see the monkey and the gorilla, that what we got here. Now those two got separated because now we got one more cluster, and they got their own cluster here. Now you have now one cluster related to the girl, which is or baby. This is also related to the baby, and this is also related to the baby, right? So all the sentences related to the baby, they got their own cluster, and the two animal related, which is related to the playing with drums, got their own separate cluster, and then you have other animal related cluster here, and then one with the eating. So this is how you could see how powerful it is. It is able to preserve that semantic meaning in the real world into that vector representation, and you could do a lot of different kind of things to solve the real world problem. Yeah, this is what I wanted to cover. So what did we cover today? So we talk about the sentence embedding, nothing but converting your text into the numerical representation. Once you have a numerical representation, you can calculate sentence similarity using the cosine similarity kind of metric. And since now you are able to calculate a similarity between the every possible pair of documents, you can build a semantic search capability where you take the query or the question, you find its embedding, and then you compare that embedding with your thousands of documents present in your, let's say, document store. And then you can find the most relevant document to your semantic search. And I have also shown you, you can take that thing to the next level. You can combine your semantic search with the question answering, and then you can build a question answering for your all the documents, right? It will become the two-step process. The first step is actually ranking existing document by using their embedding. Then you select the top document, pass it to the question answering model, and then you get the exact answer for your question. That's what we saw. And the another application of embedding we saw is the clustering. We take that vector representation, we group those clusters, and we could see we are able to group the sentence with the semantically similar into the same group. Now, these are just couple of few examples. Now you could see this is one of the important point. We fit that embedding to a clustering algorithm. You could do same for the classification algorithm also. Instead of this k-means, it could be logistic regression, random forest, or XGBoost, because ultimately you have converted your embedding into the your sentences into the vector representation. Now you could fit to the any algorithm. So you can try a lot of things. You can try the classification algorithm or all different sorts of things you could do with these embeddings. I hope you found this video useful. If you haven't subscribed to my channel, please do subscribe. I do create videos related to the natural language processing, which includes libraries like a sentence transformer or the Hugging Face transformer, or sometimes building application using the conversational AI or a GPT-3 kind of stuff. And most of my videos are related to, you can think of like project based learning or the application oriented stuff. So I try to do something in the video that you could use in your job, or you even use that skill set to work as an independent freelancer. Okay, thank you very much.